Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Zhiwei Chen and Youjun Liu with us today. Hello there.
Hello, Frank.
Oh, you're here. We were having a little bandwidth issues earlier, people. So bear with us if we get it, but it's all good. You guys look great. Where are you two located at?
We're at Peking in China.
Okay, very good.
It's close to the bird nest.
Yes. Very good. And it is, well, it's my March 6th, 2024, as we record this. It is their March 7th in the morning. And Beijing. So you guys just had your spring festival this past week or so? Yeah?
Past, I mean,
2 weeks.
2 weeks ago.
2 weeks ago.
2 weeks.
Okay.
Spring festival.
Is there any snow on the ground in Beijing?
We can still see some snow here. Yeah.
But most of the snow is melted.
Okay. Very good. Well, here in Phoenix, I'm in Phoenix. There's no snow on the ground. I'm in the desert, but it is warming up. Spring is coming. Some of the first flowers and trees are starting to do their blooms, and it's very pretty.
Yeah.
Very nice. So very cool. And let's see. Let's start with Zhiwei. What do you like to do for research?
Yeah, I'm mostly majoring in the gravitational wave astrophysics, but also the tidal disruption events, such high energy astrophysics. I think these events are very, very interesting, and it may reveal some very important physics in the such high energy scale, right?
Cool. And Zhiwei, are you a graduate student?
I am now a PhD candidate in National Astronomical Observatory.
Okay, very good. Congratulations. I look forward one day to calling you Dr. Chen.
Yeah, thank you.
Very good. And Youjun, what do you like to do for research?
Yeah, I'm mostly working on the gravitational wave astrophysics, black hole physics, high energy astrophysics, and so on.
Very cool.
Yeah.
Very cool. And that is going to bring us to this very awesome APJ article.
Yeah.
It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Detectability of strongly gravitationally lensed tidal disruption events. And Zhiwei and Youjun, take us away.
So thanks for the invitation of Frank, and I'm very happy to introduce our recent work on the lensed tidal disruption events. We have seen that more than 100 tidal disruption events have been detected as multiple bands. You can see that like the X-ray or optical and UV observations, you see a large amount of TDs. And we have known that in our universe, there are a lot of galaxies, and these galaxies can be intervening lenses to deflect the lights of the TDs. So in this paper, we first investigate the detection rate of such special TD event that is gravitationally lensed by intervening galaxies.
Interesting. Okay.
The question I want to answer is whether such kind of lensed TDs can be detectable or not.
Yes.
Whether we can fund it by large facilities.
Okay.
And I think the importance of this paper is that first we answered the question, like Professor Youjun have mentioned, will the large facilities in the future observe such special lensed TDs? And I think another important issue is that these TDs can be used as an early warning for astronomers to investigate the early behavior of the light curve of the TD,
right,
which may reveal the early stage of the mass accretion or the superident wind.
Yes. Okay. I'm with you.
So you can see that in this paper, we firstly actually this is a semi-analytical paper, and we first introduced the method to estimate the detection rate of TDs by the galactic dynamic approach to estimate the cosmic assumption rate of the TDE, and then the special modeling of the light curves of TDEs.
Okay.
And with these two recipes, we can do length statistics, and you can go to the next page and see the TDE distribution.
Okay, we generate the TDEs. Okay, good. Okay.
You can see figure 1. In this figure, we plot the evolution of cosmic TDE rate estimated by the third author of this paper, Dr. Yunfeng Chen, and the method is mainly is by the solution of the Fokker-Planck equations by the two-body scattering and the relaxation scattering, and you can estimate such a cosmic TD rate, and you can see the evolution with the redshift that is shown in the dotted line in this figure. You can see that the peak is around redshift 1.
Yep.
And it declines with increasing rate, right?
Right. Okay.
The total number of the TDE is quite high that we can detect once per year. You can see it's
wow. Yeah.
TDEs that can occur in the universe.
Yeah, that's quite a number of them. Several million per year. Okay. Okay, good. I'm with you.
Yeah, you can.
Then
we show the we try to model the detailed physics of each TD sample. So you can scroll to the right side. There is an equation. That is equation 1. You can see that we consider the disrupted star to be a typical main sequence star described by the polytropic stellar model. And with this model, we can estimate the tidal disruption radius of each single TD sample by solving the Lame-Emden equation.
Yes.
Which describes the equation of state of such a star.
Okay.
Then we use the initial star mass function proposed by Krupa. You know the Krupa initial mass function to estimate the mass distribution of the disrupted stars together with our evolution of cosmic TD rate. We use the Monte Carlo sampling method to generate such large TD samples with different parameters, including the mass of the black hole, the redshift, and the stellar mass, and the radius of the star. With these parameters, we can further estimate the light curve of each TD sample. Then we can do the length statistics.
Okay, right.
We can go to the next page.
Good.
To find out the light curve model in this paper.
Yes, we need some light curves. Okay. Where do you want to go here?
Yeah, you can see equation 5. The
fallback.
The most important key parameter in the light curve model is the mass fallback rate.
Right.
Which is denoted as the MFB dot MFB. And this parameter describes the mass per second that fall back to the accretion disk of the massive black hole.
Okay.
And also the material is comes from the disrupted star.
Yes.
And in this paper, we consider the light curve to be dominated by two isolated components. The first one is the supereditor wind. You can see that in equation 6. And we assume that it is launched at a certain distance away from the disk. And we find out the photosphere radius of the wind. And you can estimate the luminosity of such component by the black body radiation. You can see that in equation, you can go back in equation 9.
Yes. Yes.
And then,
okay, adiabatic, I'm with you. Okay, super. Yes. Okay, I'm with you.
on the other hand, I see I have said that there are two components. Another component is the disk, the accretion disk. And in this paper, we follow the steady slim disk model proposed by this paper, and we assume several conditions to meet the requirement of adopting the simulation result of Straba and Carnot. That is equation 10.
Yes.
And together with the equation 10, we assume the agent disk to be a multicolor black body accretion disk. Then you can estimate the luminosity of the disk component by equation 11, right?
Yes. Okay, I'm with you. 11.
And notice that instead of simply summing up these two components, the luminosity of the disk can also be reprocessed by the supereditor wind. You know that disk, most of the photons are in the UV or with even higher energy. Then it can be reprocessed into the optical radiation, and which contributes to a very important part to the optical light curve. So in this paper, we also consider the reprocessing process.
Okay.
So, and to estimate such a TD with very high redshift, so the K correction of light curve is also should be taken into consideration.
Yes.
You know, because the redshift effect. And we summarize the parameters in our light curves and the TDE models in table 1. You can see in the upper panel, maybe you see the 5 key parameters, which is the intrinsic parameters of the TDE samples. That is TDE redshift, the massive black hole mass, and the stellar mass, and the radius of the disruptive stars, and the penetration factor shows the orbital dynamics of the stars, which is very important. TD. And this parameter is directly related with the mass fallback accretion rate.
Yes.
Okay. And the lower 3 parameters are the parameters in our phenomenological light curve model.
Good.
First one is the radiative efficiency, and the second one is the wind velocity, which is directly linked with the temperature of the supereditor wind, and the third is the energy fraction of the wind.
Okay. Good.
And by these 8 parameters, we can estimate the light curve of each TD sample, such as in figure 2. You can see that. You can see that the early behavior of the let me first introduce this figure. It seems too complex. So the dashed line here shows the wind component in our light curve model, and the dotted line you can see it is quite flat. It is the disk component.
Right. This one.
And the total light curve is the reprocessing of the post reprocessing light curve of the wind between the wind and the disk plotted in the solar line here.
Yeah. Mm-hmm.
And you can see that in the early stage of the TDE, the light curve is dominated by the wind component.
Yes.
And you can see that it declines very quick in after the peak.
Yeah.
Then the disk, then the multicolor black body disk dominates the light curve.
Yes. Yes. Uh-huh.
And you can see that there are three colors of these lines, which corresponds to different penetration parameters in our model.
Okay.
And you can go and with and this figure is only is an example of our TD light curve. But for the large amount of TD samples we have generated by the Monte Carlo method,
Yes.
We can estimate the light curve or the we call the transit behavior of this TD sample by such a light curve model, and then we can do the lens statistics.
Yes.
You can go to the next page.
Actually, I want to back up. I'm not. Do we have an equation with beta in it? I want to see where beta is coming in.
Oh, you can see equation 4.
4. Thank you. And here we go. Okay. Okay. Let me just get this. Okay, I'm with you. I'm good. Thank you. Okay.
Yeah, you can go to the next page.
Uh-huh.
You can see equation 12.
Yes.
Yeah. So we have noted that the galaxy strong lensing is mainly due to the elliptical galaxies. So we adopted the synchronized isosomal ellipsoidal profile plus external shear to be our lens model as the galaxy strong lensing.
Okay.
And in this model, we can see that the most common circumstance is the double image case.
Yes.
So that is to say, you can see two. If the TD is lens, you can see two images, two images of the same TD. That is to say, you will have two light curves, independent light curves.
Yes.
And to estimate the detection rate or to do the lens statistics, the key quantity for such the lens rate is the lensing optical depth. In equation 12, you can see that this optical depth is mainly dependent on the cross section of the lens marked by S critical. And the velocity dispersion function (VDF) of the intervening galaxies.
Okay. Okay.
And in this paper, we adopted the observational constraint of the such VDF for elliptical galaxies, and to estimate the optical depth for each TD sample.
Okay. Okay.
Yeah.
With you. We're good.
Can go back to figure 1 to see the distribution, to see the evolution of optical depths.
Good. Good.
It is marked by the dashed line here.
Yes.
The optical depths. And you can see that the larger the redshift is, the optical depths, the larger the optical depths. This is due to the accumulation of the galaxies in the line of sight, right?
Yes. Right. More stuff.
So you can also see that from this figure, the fraction of such lens TD is generally 1 in 1,000, right? 1 in 1,000 or 1 in 2,000, such a rate.
Okay.
And you can go back to the lens statistics section.
Yes, I will. 1, 2, 3, and lensing statistics. There we go. So we finished up the optical depth in equation 12. We took that in figure 1.
And then you can go to the next page.
Luminosity function.
There is a figure 3 I missed to introduce. Actually, this figure 3 is the main goal of this figure is to validate our TD sample and our light curve model, as we have mentioned. So we use a female logical light curve model, and our TD sample is generally calculated by the theoretical galactic dynamics. So
yes.
So we have to check the consistency with our current observation, right?
Yes.
So it is what astronomers usually do. So in this figure, we plot the luminosity function of the MOC-TD population within redshift 0.2. That is the largest redshift we have observed for current TD observations. So you can see that marked by red points with arrow bars, that is the observation obtained from Van Velzen 2018, and the dashed red line shows the recent feature results of the from the observation by Yao 2023.
Cool.
And you can see that with our population, with different black hole mass and penetration factor parameter,
yes.
The general behavior of our luminosity function is almost consistent with the observation. So we think our TD sample and light curve model are reasonable to estimate the Leinster detection rate.
Yes, I agree.
So you can go to figure 4
to
show our final result of the Leinster detection rate.
Okay, and dot.
You can see that the detection rate of the Leinster TD is very related to the penetration factor marked by the dashed and solid lines here. If you adopt the 1.85 model, the detection rate will be much higher. And you can see that the detection rate in each band will not differ so much, right?
Yeah.
And the general behavior of the detection rate, you can see that the larger the limited magnitude of the telescope is, the higher the detection rate will be. That is reasonable.
Yeah, it's also quite a number of order 100, yeah?
Yeah.
Order 100 for M25, yeah.
Yeah. So cool. With this limited magnitude, it can be achieved in the not remote future. It can be achieved in the near future. So we expected the Leinster TD can be really observed or detected by telescopes.
Nice, very nice.
And when it comes to this figure, the detection rate, there is a very, very important issue we would like to raise, is about the strategy of detecting such Leinster TD, because we have seen that with future transit telescopes, we would detect hundreds of millions of TDs, and you cannot turn the telescopes to each TD and trace its luminosity. Right. So in this paper, we propose a strategy to detect such a TD with a cheap or not that expensive strategy.
Okay.
So you can see you can scroll.
Yeah.
To the last paragraph before the result. Yeah, you can see this. In this paragraph, we propose a strategy for searching and detecting such Leinster TDs. So first, we search the TDs in a transit survey, and this is what we usually do. And then we compared their host galaxies with the galaxy lensing banks produced by Space Sky Survey, such as the Chinese Space Station Telescope and the Euclid have been launched.
Right.
And then if the host galaxy of the TD is lensed, we may say that the TD is probably to be lensed, right? Because the TD is located in the center of the host galaxy. So if the host galaxy is lensed, then the TD should be lensed. So this is one kind of selection in prior to find out the lensed TD candidate, right?
Yeah, oh yeah. I'm with you.
And by this method, we will choose those lensed TD candidate and try to use large telescopes with deeper limited magnitude to follow it. And once both the first and second images are detected, we see it as a detectable lens TD. So this is a strategy for detecting such as TD.
Very nice. Very nice.
I would like to add a little bit, right? So now we have the JWST, right? James Webb Space Telescope, and we will have Nancy Grace Roman Space Telescope and others, right? For those telescopes, they can reach a very deep, right? Can penetrate far away distant universe, right? With redshift higher than a field. So that is possible to use these large facilities in the future to get to the detection of the secondary image, right? That confirms the lensed candidates. That's good, right?
Yeah, that's very good. Okay, cool. I'm with you.
Yeah, we may go to the next page to
4, 5. We got our cumulative
figure 5. You can see in figure 5, we show the time delay between the two images of the lensed TD, and and the time delay here means that the two light curve, you can see two transient behavior in the same sky area with the same TD. So you have such time to monitor your telescope. Maybe if you have enough money, you can turn the JWST to that sky area with 10 times 10 days preparation. So the time delay of lensing of the gravitational lensing provides human a natural time window for us to monitor it.
Yes. Okay, that's important.
So for such a long time delays, right? We even know when the second images come to us. So that's very important, right? We can put our telescopes directly to the place for the candidate to see, right?
Yeah.
To have a very deep exposure to see the second one.
Yeah, because we have noticed that we have mentioned that in our strategy, we should first match the host galaxy of the TD in the galaxy lens banks. And by the observation of galaxy lens, we can reconstruct the lens system and estimate the time delay.
Yeah, right.
Good.
So we can predict the time of the second image. So so we can turn the telescope in a very certain time window.
Yes. Very good. Yes, I'm with you. That's very cool. Very nice.
And you can go to the conclusion and discussion part.
Cool.
We have discussed the importance of such TD to raise its scientific values for detecting such special lens TDs. So in the second paragraph, we see that we mentioned that if one could observe the full light curve of the second image, because we have the early warning of the first image, we can use more powerful telescopes to trace its early stage behavior.
Nice.
Then we can constrain the physical process in the early stage. And moreover, this early warning may enable the pre-peak like UV optical X-ray spectroscopy observation, which is, however, very rare in literature and our observation.
Very rare.
Yeah.
Yeah, that's
for example, this additional information can be very, very useful. The first one we mentioned that is we can use this pre-peak spectroscopy to classify the TD type by the Barmore and Bowen lines.
Okay.
And it is very and secondly, if you can see the pre-peak evolution of the emission line, then it is possible to determine the change of the velocity and opacity of the super-Eddington outflow.
Okay.
Because you can examine the line width and the intensity, right? And this information is very crucial for comprehending the accretion physics embedded in the TD.
Yeah, absolutely.
And third, I think the most important application is to distinguish the to distinguish the mechanism of the origin of optical flares, because there are two scenarios. The first one is the shock and the circularization scenario. And in this scenario, there will be an X-ray in the pre-peak observation.
Yes. Okay.
Because of the shock, right? The tidal debris, the tail and the head of the tidal debris will collision to each other, and there will be X-ray emission. However, in the reprocessing scenario, just as in our paper, the X-ray is almost reprocessed by the super-Eddington wind into the optical, so there will not be early X-ray emission. So by the detection of such length TD, we may capture the early behavior of the X-ray in the X-ray band. If there is a X-ray emission, so we may rule out the reprocessing scenario.
Exactly.
But this may go much complex, but this is a brief discussion.
Yeah. Yes. Good. Great.
So in this paper, actually, in conclusion, in this paper, we estimate the detection rate of length TDs. And this is the first paper to do such a research. And then we estimate we expect with future telescopes we can detect such length TDs more than 1 to 10 per year. And in this paper we provide a completely new strategy for searching such special length TD. So this is the main goal of this paper. Okay.
I think you reached your goal. Very cool. Very cool. Very nice. Zhiwei and Youjun, I want to thank you so much for walking us through your very lovely APJ article.
Yeah, thank you.
Thank you, Frank.
Sure. And you touched on it a little bit there as you were going through. So let me push on it a little bit. Where do you think we go from here, given the published article? Obviously, some of these telescopes are going to come up and you're going to be getting a lot more TDEs, so it'll allow you to test your model. Are there improvements to the model that could be done? So just sort of what are next steps in this detecting TDEs by gravitational lensing? Where's this going? If you had to write a second paper, what would it be? Let me phrase it that way.
Right. So there are a few things that we can do, right? First one is actually we can can improve the model for the light curves a little bit, right? To consider more details about the radiation processes, and that would make a little bit change of the luminosity function, but that won't change much about the length TDE rate, I would think. So, but anyway, we can improve these kind of models to make more precise predictions, right? So the second thing that one can do is, for example, we will have the Rubin to be online very soon, and in a few years we will have Euclid, CSST, and Raman, right? So this kind of actually they are all can detect quite a number of TDEs, right? So that accumulation of the TDE number would become much more larger than a few hundred, even thousands, right?
Yeah.
That's the expectation. So with this kind of detections, how can we search for the length TDE, right? We believe it will be ultimately detected, but how can we search it? How can confirm such kind of events? We can combine with those facilities and our models to investigate a little bit more to quantify how many and when we will detect such kind of events, right? So this is the second thing. The third thing is once we detect these kind of events, how can these events be used to distinguish different TDE models? As you know, TDE models are actually very complicated. There are lots of uncertainties actually, right? As you can see, the luminosity function of our figure 2, right? So it's quite a large uncertainty, right? You see that because the parameter choices such as the penetration factor, etc. Right? So then one could use combine with I mean first one and the second one that can be done, right? Combine these kind of works to see whether can we really distinguish those simple window model reprocessing processes and put a strong constraint on these kind of processes, right? So that would be that can be done, right? We will do this kind of stuff.
Very cool. Well, it's going to be really exciting over the next couple of years as these facilities come online and you actually get to test your model. It'll be very cool. Very nice. So I really look forward to seeing that develop over the next couple of years. So, well, go ahead.
Yeah, so the other things is not only the optical observations, but also there will be other observations. For example, right, you know, the Einstein probe is was launched a few months ago, right, in China.
Right.
Just in January 9, right? So it's determined to discover TDEs, right? This is the most important part for its science school, right? So we will also see lots of X-ray TDEs, right? That we could do for this paper. We only consider about the optical TDEs, right? But you can also extend it to X-ray TDEs.
Other bands, right? X-rays.
What would we be see? Yeah. So
exciting. Exciting. It'll be very exciting.
I would like to add more on the observational side. Maybe first we can construct such a galaxy lensing bank, because that is very important in the strategy for searching such lens TD.
Yeah.
And also the lens stellar binary black holes in my other works, because the stellar binary black hole also have no electromagnetic counterpart. You have to find out the host galaxy. So the importance. So I would like to raise the importance of construct such galaxy lens bank.
Yeah.
And I have also talked with the with guys doing observation on TDs, and they have said that they are now prepared to find out such lens TD by the WFST. You know this telescope.
Battlefield
Transit survey in University of Science and Technology of China. It is a 4-meter telescope.
2.5.
Oh, 2.5.
Yeah. Somewhat
2.5.
like a PDF, but it's 2.5.
Okay, nice, very nice. Cool, exciting times, yes?
Yeah. So for transient.
Yes. Otherwise, it's boring. If it's not transient, it's boring. And it's just sitting there. So, very cool.
Large message astronomy is blossom.
Yeah. Oh, yeah. No, we're in a golden age here. It's really fantastic. It's
All right.
Zhiwei, Youjun, I want to thank you so much once again for walking us through your very lovely article. Appreciate it.
Yeah.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Yeah.
Thank you.
Thank you,
Frank.
Thank you, Frank.
Mhm.
See you.
See ya.